Hello, everybody. Sorry for the slight delay. I was having some problems joining the Zoom, so it was a bit delayed. So I'm going to talk about BEAMJIT a bit and some of the things that we have done in that project and some of the things that we have found during that project that are part of upstream Erlang OTP at the moment. Talk about these things and talk a bit about the future and what that would bring. This is a relatively short talk, so there will be time for a lot of technical details, I think. But we'll see. Let's see if I can switch it. So first I'm going to give a quick overview of what a JIT compiler is and how they're used. So normally what they do is that you optimize code while the system is running. So while you have your system running, the system looks at what code is being run and tries to find ways to optimize this. The most obvious way to do this for a runtime such as Erlang is that we have a higher level instruction set that we try to convert into running specifically for the CPU that we're trying to run for. And we just convert this higher interpreted language into lower level assembly code and make the system run that instead. We also apply some kind of optimizations based on the profiling. So when we know what code paths are more likely to be taken and these things, that's what the JIT compiler really shines, because it can do online profiling in a way that an ahead of time compiler cannot really do. And it can also, of course, adapt its patterns depending on your current system's needs. So for instance, your daily runnings of a system might be very different from when you're under a distributed denial of service attack, for instance. You have different optimization paths depending on what the system is being subjected to. Some famous examples for just-in-time compilers is the hotspot Java virtual machine, has been a long time, V8 for JavaScript, which is the Chrome, Google JavaScript engine, CLR, which is the C#.NET JavaScript runtime, and some maybe not as famous, but equally good is like the SpiderMonkey toolkit, which is Mozilla's JavaScript things. The PyPy engine, which is a very, very interesting JIT from a theoretical standpoint, at least, and it's really good for from performance as well for Python, but it has problems, as all JIT compilers. And the Lua JIT is also a very, very interesting machine in the way that it works, I found. So the basic method that every JIT compiler uses is that it does some profiling, then it compiles the higher level code into some kind of lower representation. Could be native code, could be something different. And then they run that code, and then you profile again, and then you compile and you run, and you do this cycle over and over again for different functions, modules, classes, whatever you have. So for instance, like the JavaScript JIT compilers would profile executing like the abstract syntax tree of the JavaScript files first, and then when a function has been called more than once, they compile that into something that's interpreted. So they do one tier of the JIT there, and then when something's been run 10 or 20 times, they compile that into native code, and then when that's been run 10,000 times or something like this, they optimize that native code a lot. So you have multiple tiers in the JIT doing different parts. And this is basically what's called a method JIT. So you compile one method at a time. There's also a class of JITs called tracing JITs, which work very similarly, but it's a bit different. So you profile, and you trace the execution pattern, and then you compile it and run. So instead of taking a function at a time that you compile, you look at a execution trace, so a common path within the code that is being run, and you take that execution trace and try to optimize that specifically there. So these different approaches have different pros and cons and present different difficulties when you are trying to implement something like this. So for the method-based JITs, they are very similar to a normal compiler, which makes it a lot easier to write these kinds of JITs in some ways, because you can get a lot of knowledge from the ahead of time compiler community, because it's the same kinds of problems that they are trying to solve. But you need to do it faster, a lot faster, because you're doing this in runtime instead of doing it offline when you have almost all the time in the world there. The hard parts, as I see them, between the trade-offs between these things are that in the method-based compiler, the hard part is figuring out what type of inlining decisions should you be making. So you're compiling one function as a unit, but you want, in order to get speed, you want to have inlining in this, and deciding what parts of the system you want to inline into a function, what the trade-offs are there. That's really the hard part of figuring out how to make a good method JIT, because inlining can make things a lot faster, but they can also make it slower, and it's an expensive computation to figure out when you should be doing these things. And for tracing JITs, deciding what traces are hot and what paths you want to compile is very, very difficult to figure out and get a good heuristic for. So talking a bit about BEAMJIT, our implementation of this. So our goals for BEAMJIT was that it's supposed to be very easy to maintain. We are a relatively small team. We are at the moment 6-7 people working on the Erlang virtual machine and the standard libraries and kernel and these things, the core parts of it there. And then we have like 6 or 7 people working on the protocols and network and other things. So there's not a lot of people to work. So we have to have something that's easy to maintain. Basically, one person or possibly 2 has to maintain this forever. It should never be slower than the regular Beam. It should be identical in functionality. And one of the goals we also had was that we wanted to be able to optimize across module boundaries there. So we've given talks about these things before at conferences. So in 2012, which is 8 years ago, now I did a small intro, and this is basically when our efforts started. There, we have been not working full time at all on this. This has been a research kind of project that we do when we have the time or when we have good ideas for different parts. There, we did a first version that was using a library called libclang. There's a presentation with a link that will be in the slides that you can go and look at. That a research partner, Fred Reiheimer, did that uses that tries to automatically slice up the main emulator loop in small chunks using a C analyzing tool. So it tries to parse the C syntax tree and does this automatically. We stopped with this version in 2015, 2016, something like that, because it could not deliver on the performance we wanted, and it was really, really expensive to do context switches between interpreted and native code in this version. So we started another version, which is based on LLVM IR. So it's at this point, some tools went into the LLVM compiler toolchain that we could use, and then we tried to use those. And you have a presentation there with the link as well if you want to know more about this version. And we have a third version, which is the one we've been working on most recently. There's no videos on this one, and it uses a more specific IR version that we have designed ourselves, because we had a lot of problems trying to maintain the LLVM IR version, as the emulator would change behavior depending on how you wrote the C code. So maintainability could not really be achieved with that LLVM IR version there. And in December 2019, we decided to pause the project of a JIT compiler for now and focus on a head of time compiler instead. So that was kind of a sad day for us when we decided that now we've spent all this time, we have to realize that we can't achieve this at the moment. So we're going to focus on doing what we know, which is the head of the compiler, so the Erlang compiler. Some of the things, takeaways that we have from this is that creating a JIT compiler for micro benchmarks is very easy. Creating a JIT compiler for real workloads turned out to be very, very hard. And this is what we've been struggling with. So small benchmarks we do very well in all of the different JITs. But doing something like taking it onto a real system and trying it out there and getting performance gains that are measurable there is very, very hard. And we have not been able to do that in none of the versions. While looking at like real workloads and such, we realized that predictability is very, very important. And the way that we structured all of these JITs, it was hard to predict the performance. It was very random if you would get good performance or if you could possibly get bad performance, depending on timing issues and such things, which traces were created and so on. We also, unfortunately, not unfortunately, but we relied quite heavily on the tooling present in LLVM. For instance, in the LLVM IR and also in the Beam IR versions, we used LLVM's stack map support quite heavily. And that's an experimental feature within LLVM, which we, in hindsight, we shouldn't maybe have used because it meant that we spend a lot of time patching LLVM support for it and making it better and so on. Many, many hours were looked at trying to make the support work for us, and it didn't end up doing that in the end. All of our different compilers were trace JIT compilers. So tail duplication is something that was very hard for us to get right. And we also realized that Erlang code is a very, very branchy code, which kind of goes against the whole trace compiler concepts. And it makes trace compilation a lot more harder to do. So what did we do that was good? So I'm going to go through some of the changes that went into upstream for this. I want to check what my time is so I know what time. Yes. So we did profile guided optimizations, which is basically running the C code and trying to figure out different parts. The reason why we did this is because we realized when working with LLVM Clang, that Clang is not really a good compiler for compiling the Erlang emulator. As you can see in this benchmark graph, there's about a 15% degradation in using Clang when you're compiling Erlang. So on all the Macs and everything, Erlang is generally 15% slower just because you're using a different C compiler, which is not a good thing. So we found out that you can do profile guided optimization on the C code, or we knew this, but we found out that this actually makes it better. So where does this performance go? So if we look at the Clang 6 code, there's part of it compared to the GCC 6 code. There's a small part here that is the culprit for this specific instruction. So this is a read from the stack that's not part of the GCC code there. And this is a read of the X register array. So this is something that happens in almost all instructions within the emulator. And this costs a lot of performance. And what decisions the compiler actually makes in order to figure out what to do these things is very hard to figure out and very hard to direct to do different things. But if we turn on profile guided optimizations, we can see that Clang moves up a bit. So the blue part here is Clang and the green part here is other things there. So it helps a bit. And if we look at the assembler, it has actually eliminated this read from RSP, and then it uses a value directly. So that's good. Now, this also varies across different versions of Clang. So Clang 6 is quite old. So what happens in more modern Clangs? Well, things go a lot worse in modern Clangs than the old Clangs for some reason, at least when you download them for Ubuntu. On the Mac, it goes a lot better in modern versions. So there's a lot of differences between different operating systems, how you compile Clang and what is in there and different things. So doing this is hard and it will vary a lot depending on what the things you are. So for instance, the same instructions using Clang 11 on my thing turns out here and it doesn't even fit on the slide. There. Sorry, I'm going a bit quick because I'm kind of running out of time there. So we also did another thing called instruction word packing, which is for the keen observer. you might have been able to spot that there's a bit of a difference between Clang and GCC in the ingress of all of the instruction. The main part is that there's 0.4 here and 0.10. So that's a way that we've started to pack our instructions in order to fit them better into the memory of the virtual machine. So the normal opcode dispatch loop looks something like this. So you read an opcode, you do some work, you increment the program counter, and then you loop again, over and over again. As an optimization, this code actually looks some bit more like this. So you do some work, you increment the program counter, and then you jump to the next instruction instead of looping in a while loop. And this gives about a 15–20% performance increase doing this trick here instead of doing it the other way around. But now we're jumping to memory addresses, which means that for the memory layout, this will take an entire word, and then you get the arguments to the instruction on the other side. There. So can we make this better? It turns out that we can. So instead, when building the emulator, almost always all of these instructions end up in the lower 32-bit memory area. There. So we jump to the pointer as a 32-bit pointer instead. This means that we can do the work and jump to the next instruction in the same thing, but we can start packing these as 32-bit integers instead, and then we can move the arguments, and we save roughly 15% memory usage in the loaded code, which means that we will fit in smaller caches, which means that it will be running faster. So this is a good thing. Let's see. Another thing in the same area that we did was that we started doing relative short jumps instead of doing absolute short jumps. So a local call before OTP21 would look like this. You do a call, and then you have an address that would be an entire word to where you would be jumping. But local calls are only within one module. So what we can do then instead is that we can do relative calls in these parts. And instead of doing what this says here is that we set up a call frame, and then we write the program counter to where we want to jump, and then we do the actual jump. So instead, we change this to be an increment of the destination, and a module can only be so big. So this is a limit on it. Now it can only be 2 GB of code, which is already a limit before. And we can do the jump, and now we can pack this even further, so we can make smaller instructions, and this again makes the code smaller. Another inspiration that we got from this is the new compiler internal format. So this came in OTP22. You can read more about it on our blog. There, it introduces an SSA, which means that it's a static single assignment phase within the compiler. Basically, Erlang code before this looked something like on the left. You do an is list on a register, you do a get list on that same register, and you put it in the same destructible register, and then put it in another register, and then you do a get head in the X1 and put it in X1, and then you do a plus on X0 with X1, and then put it in X0, and then you return that value. So instead, in SSA form, this would look something like this. It's a bit more verbose, but in here you can't reuse variables or registers in the same way. So the is list, and you have a branch for different parts and so on. So this is heavily inspired of what the syntax for how the LLVM IR looks like, and the semantics and so on are very similar to this. And the main advantage for us here is that we have a delayed register allocation happening, so we can do more low-level optimizations on this code. There. So this caused us to have improved binary matching, so we can now match things a lot easier. Improved typed optimizations, and we can also now lower fun calls, so that when you do a fun call that we know is only done, is the fun entity is actually never used, we can just flatten that and make it a normal call, which saves a lot of heap memory and so on, and makes it a lot faster. So I have some benchmarks to show you for how this works in practice. So this is the Unicode module normalizing some Unicode parts. And we can see here that this, for this graph, higher is better. And the dark green here is where we are with the master branch. So this is steadily going up, which is good. The main tier is the maintenance branch. That's kind of the maintenance releases, and these jump up to sync with the master branch for every release, major release that we do. And then you can track the different individual releases, like the main 21 release goes down here, and we can see like the main 22 release is released here, and then we start tracking it. So for this one, we're almost at almost twice as fast, not really. And here for binary look ahead, we can see that we get an incredible dip here. So this benchmark lower is better, just to confuse you all. So we can see that on the main TOPU main branch, we get a huge dip when we release OTP 22 here. So this is the SSA part, and the master branch just keeps ticking along here. So this is almost 3 times faster, which is nice. We also do for floats. There's a lot of changes, and we can do things. This is maybe a 25% better part for the master PU. And Mandelbrot computations are also floats. So this is the same thing. So what is the next thing that we're talking about? Let's see how much time I have left. Not much. So I said that we were going to focus on the compiler and trying to figure out this. And as most, I'm very interested in JIT compilers. So about 1 week after we made the decision to focus on the compiler and not do JIT compilers anymore, I started working on a new JIT compiler. So this is a simple method JIT that we started in January 2020. I was working on this on my free time because I like working with these kinds of things. And now in May, we have 99% feature parity. We have some small features missing, but tracing, code loading, all the difficult things are there. We pass 100% of our tests suites in there. Our performance is about 25% increase over normal Beam, which is a good thing. We are never slower than this test case, but we'll fix that eventually. Compared to our previous results here, we have the BEAMJIT as green, and we have Hype as orange. And we can see that interpreter is slowest, BEAMJIT is maybe 10% increase, the new method JIT is maybe 20%, and Hype is somewhere around 40%. And Hype really, really shines in some few of these benchmarks that are micro benchmarks. And we will talk more about this new method-based JIT on CodeBeam Stockholm, I hope. If in person, if possible. If not, we'll talk more about it online. That was it from me.
Thank you, Lukas. Big hand. Virtual, real. No, but this is awesome stuff. I mean, I think this the just-in-time compilation is the holy grail of compiling, right? So this is a very, very interesting topic, and it's great progress that you've made, and you've learned a lot, obviously. So let's go to the Q&A. I'm looking at Hoover. We have a question from Robert Ellen. And it's, is there a risk with just-in-time compilation that you can produce too much native code and have problems with cache performance, etc.?
The answer is yes. We've seen when benchmarking, we have seen that like the instruction cache sizes of the different CPUs greatly affected the performance we had. So when running for the Beam IR things, we had 2 different machines doing benchmarking on, and for some benchmarks, when we were able to fit inside the cache, we were really, really fast. But then on some ones when we were not, we couldn't do the same. So yes, there is a problem you get when you get a huge code sizes in there. For normal applications, I would say that this is kind of what happens in an ahead of time compiled environment anyway. So when we're competing with the ahead of time compilation, this is the same problem really that they try to work with there. Yeah, when working with an interpreter, you do get smaller I-cache pressures, but you do get a bigger D-cache pressure, which makes the D-cache slower, which makes producing terms and all the other things a bit slower. So it's trade-offs as always.
I think we have time for one more question from the virtual floor. We have a lot of people attending, so thank you all for coming. Don't be shy. I think you can unmute and ask Lukas one final question.
If there's no one else, I do have a follow-up question.
Yeah, please.
One of the things with with VMs that do with the switching is that that's really bad in terms of branching performance, and you get pipeline stalls. Is there any work to try and overcome that? Like any research to try to with branch prediction and that sort of thing to try and stop that? Because yeah, my understanding is the switching that you have in a register-based machine is really, well, any machine is pretty poor.
So when you try to research these things, there's a lot of papers that come up from like 2005, 2006, 2008 that talk about lots of different strategies of trying to make the branch predictor work better for an interpreter in different ways. Fortunately or unfortunately, at least Intel has gotten a lot better with the branch performance heuristics since then. So we have tried different varieties of trying to make the branch predictor work better for us there, but at the moment we can't beat the way that, or we can't write our code in a better way that the really good branch prediction algorithms can do something with. We haven't benchmarked a lot on other architectures than the Intel architecture, but at least their branch predictor has, I mean, they have a history buffer where they keep track of where the code is coming from and so on. So trying to beat that is not really possible using other methods like using call threading or using something different than that. So it's, the CPU is really good at trying to figure out what branches to do in different parts there, and we haven't found a method to make it do better things for us.
Thanks.
No problem.
So thank you again, Lukas, and thank you, Robert, for good questions.